In this video, I'm going to go over what function transformations are, what they look like, how they're graphed, and how we can write their equations. So to start, I'm just going to go over the three major types of transformations. So the first one is a translation. So this means you're shifting the graph left, right, up, or down. So as far as notation goes, if you have something that you're adding to x inside the parentheses of a function, this would result in a shift left. If you have something being subtracted from x in the parentheses, this would result in a shift right. And then those would represent your horizontal shifts. And then if you want to do a vertical shift, that would happen on the outside. That means you're really adding or subtracting the number to y. So this would be a shift up. And if you have minus a on the outside, that would be a shift down. So again, horizontal shifts occur on the inside of the function. They happen with x, and the vertical shifts happen on the outside because they're being done to y. Okay, so next we have our dilations. So dilations are when you multiply a function by something, either the x values or the y values, and this can either make the function stretch or grow in size or shrink or compress or get smaller in size. Those are all the different words we can use to describe it. So this would happen when there's some sort of coefficient being multiplied to the x or the y. So to start with, this would give us a horizontal dilation. This is also sometimes called like horizontal scaling. That's another word for it. And the thing that's a little bit strange about a horizontal dilation is that the factor you'd be multiplying all of your x's by is actually always going to be inverted. So this would be by a factor of 1 over a. I know that sounds a little bit weird, and we'll do an example with this later in the video, but essentially whatever you're multiplying your x's by, it's always going to be the multiplicative inverse of what the a actually looks like inside the parentheses. A vertical dilation is not as complicated. It's more straightforward. You're going to have a coefficient on the outside of your function, and this would give you a vertical dilation. And the factor that you'd be multiplying your y values by would just be exactly what a is, so you do not have to do that inverting for a vertical dilation. Okay. And finally, we have our reflections. So a reflection happens when there's one of the variables in the function is being negated, or it could be that both of them are being negated. So when you negate the x value in a function, so that means the negative sign is on the inside, this would result in a reflection over the y-axis. So I'm just going to use the shorthand geometry notation here. If you are negating the function itself, which would really mean you're negating the y values, this would result in a reflection over the x-axis. So really, whichever variable you're negating, you're going to end up reflecting over the opposite axis. So the first example we're going to look at together is an example of the equation of a function that has some transformations being done to it, and we're going to list out what those transformations are, and then we're going to graph them. So when we list out our transformations, we always want to do it in the order that they would be occurring, and that really just follows order of operations, but we can use this acronym, HDRV, meaning that the first thing we take into account is any horizontal shifts, then we look at dilations, then reflections, and then finally vertical shifts. So when you're asked for the order or the sequence of the transformations, you want to follow that acronym. So for this particular function, it might be nice first to identify the parent function. That means what's the most basic function that this equation sort of has at its core. So this really is a square root function. So as soon as I recognize that, I'm going to go graph my parent function because that'll give me a basis for the rest of my transformations. So if I consider the square root function, I'm going to do the easy points. If I take the square root of 0, it's 0. If I take the square root of 1, it's 1. And if I take the square root of 4, it's 2. Those are like all the easy perfect squares that I can fit on this graph. If you're uncomfortable doing that right off the top of your head, you could always put that in your calculator and go look at the table to generate some values. Okay, so now that we have that, I'm going to be looking first at this function for a horizontal shift, and I see it here with the plus 2. So the first thing that would be occurring to the square root of x would be it'd be shifting left 2. We said earlier that when you add a number to a function on the inside, you shift left. The next thing I'm looking for is a dilation. I don't see any because there's no coefficients anywhere, so I'm going to skip to reflection. Because the x is being negated, that means I'm going to reflect over the y-axis. Okay, and then finally I'm looking for a vertical shift. That occurs right here. This -3 at the end would imply this function is being shifted down 3. Okay, so I'm going to keep my colors the same for each of the transformations that I just listed. So I'm going to start by moving everybody left 2. And I'll draw that graph in, connect the points, and I'd have something like that. Now I'm going to reflect over the y-axis. That means I'm going to count how far each point is away from the y-axis and go the other direction. So that third point is actually going to go to the other side, which makes sense because this graph has now been flipped. I missed that point a little bit. That's not perfect. And then finally, I'm going to take that blue graph and I'm going to shift everybody down 3. Notice that each time I'm always going off of the last graph that I drew. I'm never going back to the original. So here is my final graph of g of x. So by applying each transformation at once, I was able to come up with the graph of the square root of negative x plus 2 minus 3. Okay, let's look at another example. So now we're going to go in the reverse. I'm being given a description of the transformations, and I'm going to come up with what the function notation of that equation would look like. I put 2 examples of this because I feel like there can be different scenarios, and I want you to see all the different things that can happen. So this first one, it's telling me that the parent function is x squared. So that means as I'm writing it, I'm going to have a quantity squared to reflect that parent function. It's been translated 3 units to the right, reflected over the x-axis, horizontally scaled by a factor of 2, and finally translated 4 units up. So to start with, in my regular black pen, I'm going to just name the function and then give myself a lot of space. I know I'm going to have something in front. I'm going to have parentheses squared, and there's going to be an x here, and then I'm going to have to fill everything else in. So first, I'm going to take care of the translation 3 units to the right. That means I have a -3 in here. Remember, when you take away a number from the x inside the parentheses, that means you shift right. The reflection over the x-axis is going to come by negating the entire function. So that means I have a negative sign out here. Horizontal scaling, if you remember, is the one that's a little bit weird. Since I'm scaling by a factor of 2, I actually put the multiplicative inverse of 2, or the reciprocal of 2, in the parentheses. And finally, translated 4 units up means I'd have a +4 at the end. And so here is the equation of all of those transformations to the parent function x squared. Okay, so we'll look at one more of these. This time the parent function is this absolute value function. We're being told that it's vertically scaled, or that means vertically dilated, by a factor of 7, reflected in the x-axis and the y-axis, so we're actually going to have negative signs in both spots, translated 5 units to the right, and finally translated 2 units up. So kind of like last time, in my black pen, I'm going to start by kind of just giving myself a shell of what this will look like. So I'm going to again just call it g of x. You can really pick any letter. And I'm going to leave a little space at the front and then put my absolute value bars with a bunch of space in between. And I know I have an x in here. Okay, so the vertical scaling by a factor of 7, that means that we have a coefficient of 7 sitting on the outside of our function. No weird thing where we have to flip that number, take the reciprocal, not for a vertical dilation. The reflection in the x-axis and the y-axis means I'm going to have a negative out front and with the x, so in both spots. Translated 5 units to the right would mean I also have a -5. And finally, the 2 units up, I would do a little +2 at the end. And this equation now represents all the transformations that are listed in that couple of sentences. Okay, last thing I want to do is just look at one more graph. So here's an example. This time I'm being given this graph, and let's go ahead and assume that this is f of x, and I'm being asked to draw on the same axes to f of x. So that would imply a vertical dilation by a factor of 2. So I just wanted us to see a transformation where you're being given some different shape. So it's not a parent function that we're familiar with, it's just using some random graph that we're given. So if I vertically dilate by 2, that means all of the points on this graph, I'm going to take just the y value and I'm going to double them. So I'm just going to kind of go to each point that I can see and then figure out where it would be. So if I go to this first point, it doesn't really matter what the x value is, but it's going down 2. I'm going to double that and go down 4, but stay at the same x value. So again, I'm really just doing a vertical stretch here. That's another way another thing we can call this. Now I'll go to my next point. Again, this is up 2, so if I double it, it would actually go up to 4. This point is only up 1, so when I double that y value, I'm only going to go to 2. So notice it's not consistent. Every point is not moving the same amount because it's multiplication. Finally, this last point is 5 units above, so its y value of this ordered pair would be 5, so I'd really be going to 10, so I am going to go off the graph a little bit, so I'm going to go up 5 more. I would land somewhere right around here. And here you can see that this graph has been stretched. It's as if you took the ends of that weird like squiggled shape and I pulled it. I would end up looking something like that. So again, it's not consistent. It doesn't necessarily look like the exact same shape because I stretched it. So it did not maintain the exact same shape after I did that dilation. So that's just a whole bunch of examples of dealing with function transformations.